In this video I will show you how to measure impedances at high frequencies with a vector network analyzer. I will illustrate the procedure by connecting our HP8720C network analyzer to 3 high bandwidth oscilloscopes from different manufacturers. Let me spot that we just want to show you how these measurements can be made and what are the typical numbers you can find. The cost of the instruments we are going to test is not comparable because they have quite different bandwidths and other relevant specifications. These are the oscilloscopes we measured. Remember that the first step is a calibration. The procedure to calibrate with our network analyzer is described in the first video of this series. We need a cable and don't want it to make any influence on the measurement. Therefore, we connected the standards at this reference plane. The connector of the oscilloscope is not of the same type of our standards, so we need an adapter, which will of course contribute to the mismatches we are about to see. Now I connect the cable with the aid of an SMA finger wrench. We fabricated it with a 3D printer. You can find a number of nice designs of this useful tool on the web. Good. Since we have switched on the averaging, the measurement needs some time to stabilize. We can speed up the stabilization of a measurement done with averaging by pressing the measure key and then measure restart. Let us check these measurements. The marker is at 12 GHz, which is the highest operating frequency of the oscilloscope. Then I can measure an impedance that has a resistance of around 42 ohm and the capacitive reactance of minus 1.8 ohm. We can reproduce with simple maths the value of the capacitance displayed in the analyzer screen, which is obtained by modeling the oscilloscope as a resistance in series with a reactance. We can do a cross-check with the measurement displayed in the logarithmic plot. To do so, we need to use two well-known equations. The first one gives us S11 from the impedance, where Z sub ost is the oscilloscope impedance and Z sub 0 is the reference impedance defined in the analyzer, typically 50 ohm. Since S11 is a quotient of voltage waves, we use 20 to calculate the magnitude in decibels. A perfect oscilloscope would have return losses equal to minus infinity at all the frequencies of its band. Let us see how much is this in real life. Writing a short script in MATLAB, we obtain an S11 of minus 21 dBs. If we go now to the logarithmic plot of S11, we can check that the value is close, but not exactly the same. The reason is that the analyzer was in free run mode and therefore we are comparing different measurements. The discrepancies are around 1%. The logarithmic plot enables us to easily identify the frequencies at which the matching is worst. In this case, the worst frequency is around 9.1 GHz, where the return losses are around 14-15 dBs. These are the measurements we made with the Yokogawa DL6154. This oscilloscope has 1.5 GHz bandwidth. Its maximum return losses are found at the highest operating frequency and are around minus 18 dBs. The third oscilloscope we tested is the Tektronix TDS3052. It has a bandwidth of 500 MHz and gives a return loss of around minus 16 dBs at the highest frequency.